So laser beam machine is it's one of the machining process, non-contact or it's not traditional, it's non-traditional machining process to remove material. Okay, because the main reason why it is called non-traditional is because it is not having a direct contact with the workpiece. Okay, as you can see from the figure or name, it's a laser. Okay, it's the non-contact type of machining process. This is the figure. Okay, apparatus or how it is arranged. We have a flash lamp on either side, and the part, this rectangular part in the middle is called the chamber or the laser light material. We are actually producing the laser light. This is not just simply uh, the light. We are actually producing. We have flashlight on either side. So when this flashlight uh, act on the laser material placed inside that chamber, it will create the electron. So de-excitation electron finally form the laser, and that laser is used to machining the workpiece placed under it. Okay, so let's look detail into it. How does laser beam machining works? So laser LBM, okay, laser beam machining uses light energy. Okay, that's not simply light energy, it's a focused coherent beam of monochromatic light. It will be having a particular wavelength and will be having, so it is a monochromatic light, focused coherent, completely uniform focused light to remove the material by vaporization and ablation. Ablation is basically melting, vaporization melting. Okay, just simply removing the material by friction. Okay, so just remove by vaporization and melting by using a focus beam of laser light. So it does not involve mass material removal. If you just use the laser light, just not simply remove all the material, by having a controlled material removal. So that's the specialty of laser beam machining. It does not involve the mass material removal, but does provide rapid material. It would remove the material rapidly, but doesn't mean remove all the material. Okay, and it is non-contact and non-wearing tool. The tool will not be non-wearing because there is no contact between the workpiece and the source. It is non-wearing tool, non-contact. Okay, laser. It's using laser to machine, right? So what does laser stand for? It stands for light amplification by stimulated emission of radiation. Okay, that's what laser stands for. So laser has a divergence. This laser coming out of this path has a divergence angle less than 1 to 2 milliradian. So this lower divergence angle makes them achieve more in intensity. So if you keep very low divergence angle would give more intensity to remove the material. Okay, by using suitable lens, because after this beam of light coming, it is passed to a lens. So this lens is what it makes to focus at a particular point. So um, by using a suitable lens, it is possible for getting enough energy for melting workpiece. Okay, so how does this happen? How does this laser light produced? Okay, what is the principle behind it? So I already told there is a flashlight placed on either side of the apparatus, and there is a laser material placed inside the chamber. And after this flashlight falls or into the laser material, it causes form laser. So what happens there? When the electron absorb the energy from the external source or that flashlight, the electron in its original energy level jump to high energy level. We know there is a laser material placed inside the chamber, so it will be exciting electrons after absorbing the energy from that external source. So electrons, which are actually in a original state, but move excite to another level, having higher energy than what is its actual energy state. So it cannot move like that. Simply absorbing energy cannot move. This is an unstable condition. Okay, it is an unstable process. Process is an unstable condition. So it will come back. Initially it is move upward to original highly excited state by absorbing energy, but it regain back to its position original position by that energy is absorbed by re-emitting. Okay, it was initially it moved to higher state by absorbing the energy from the external source. Okay, it moved to higher state, but it can't stay there because what? It's unstable condition, right? So we have to come back to its original state by re-emitting or emitting that radiation which is absorbed to move higher. Okay, that's a basic principle of basic working condition in a laser. So that radiation is re-emit finally cause to form the laser. So the atom already in a higher energy level absorb energy, it has to emit double the energy to come back to original level. Okay, we have talked about the atom at lower level that moving to higher level, but what if it is already at a higher level? Then not to come back to original state, it have to emit double the energy which will actually absorb to more higher state. So double the energy to come back to its original level. This is a simple representation on how does atom move. It's a configuration of all the electrons, a simple diagram. So atom which is supposed to actually down here, it move up here by absorbing energy from the external source. But due to this unstable condition, it go all the way back to where it was by re-emitting, and that re-emitting energy is what goes to produce the laser. So light energy of a particular wavelength is used to stimulate the electron in order to produce additional light. Yes, we are using a particular wavelength, right? Monochromatic light is used to stimulate this, right? So you're using a particular wavelength to stimulate the electron, not to produce that light. Okay, and that light produced is having the same characteristics of the original light. So suppose I am using a particular light source having a particular wavelength, and the light energy that produced would have the same wavelength or energy that I use to stimulate. Okay, that's a property. The energy emitted by atoms have the same frequency and wavelength as the stimulating energy. This is the fundamental of laser. Okay, so when the laser material is placed in process of some energy source, it absorbs and releases when it reaches the absorbing limit. That high intensity beam is called laser. So, okay, we know it absorbs, right? Presence of some energy, it absorbs and releases. When it releases, that that after its maximum absorbing limit, it release and get back to its original state. So various steps are working. Okay, various steps are working. So the laser material usually we use carbon dioxide or could be some other gas. Uh, that is placed in the large discharge tube, and we have switch on flashlight on placed on either side of that discharge tube. It will produce a light energy that causes exciting of electronic atom. This is what just I explained earlier. You should just write in steps. Okay, the basic steps are working. This is how it actually work in sequence, right? This observed energy from a flashlight causes the electron to absorb energy for excitation at a molecular level, right? So this is a representation or a schematic diagram of LBM. So the laser formed due to emitting energy is focused through a focus lens. Okay, this laser, okay, we know after from the discharge to the laser is produced by this re-emitting and discharge, okay, of electron, but the beam coming after I have concentrate at a single point, right? Not to this is coming at a parallel. I won't able to machining the workpiece if it's coming in parallel direction. I have to concentrate at a single point. So what I will do is we just use a focus lens in order to concentrate at that single point. Okay, the laser formed due to emitting energy is formed through a focus lens and directed towards the workpiece. Now the laser impinging on the workpiece start machining by vaporization melting. We know what happens when the laser falls on the workpiece. It started to machine by vaporizing and melting. Okay, this is a further close view. How does this work? This is a workpiece. The laser beam that's coming from the discharge tube, but in some laser beam machine, there will be an additional source for machining. We'll be using some cutting gases with the help of a nozzle. Normally, we only use the laser beam to machine, but in some higher advanced laser beam machine, there will be an additional cutting gas which can be supplied by a nozzle placed just above the workpiece along with the laser beam. So it will be having a higher effect or would increase the machining capability a little higher. So this is a different stage of machining. This is a this is a vertical view of a workpiece. This is a workpiece. Laser beam coming this direction. Then there's a first of all it will be having conduction, right? The heat generated will be transferred along the workpiece. So first of all there will be conduction. It will move like this direction from left to right will be conduction. Then for the heating will cause it to melting. Okay. So first it will be having conduction along this direction, but further if I keep that heating constant because I am applying constant laser is applying, so further heat will cause melting. Okay, so finally if I extend that laser beam rate, keep constant further, what really happens is evaporation will take place. Okay. So first absorption and heating, thermal conduction, then melting, and finally vaporization. Okay. This is a different stage. If I just close up and look what happens inside the workpiece. Okay. This is a various process parameters, the one which affect the machining of this ELPM. Okay. First of all, focusing of the lens is important factor. So what is focal length or focusing of the lens means the distance from focal lens to the focal spot. Okay, focal spot will be on the workpiece and focal length, and that distance is focal length. So that focal length is crucial parameter for the intensity of beam. Really matter how we get the laser beam. Okay, so spot size has to be small enough to keep the intensity high. Okay, this is all about the focusing lens, then focal position. Okay, a small spot size create high intensity, but it will only create small depth. So it won't be able enough capable to penetrate. The focal position has to be changed according to the workpiece surface. So I'll be using a different workpiece different time. I won't be able to machining same material all the time because it varies with what I'm using, what method, what workpiece I'm using varies on its characteristics property. So you have to change the focal position according to that. Next is cutting speed. Cutting speed is inversely proportional to thickness. So thickness means how much, okay, that depth at which it means cutting speed. I mean, if the cutting speed is very low, I'll be having a very high thickness of machine. Okay, so when the cutting speed increases, so I'm using cutting speed increase, it decreases the cutting time, right? So it'll be going in a very slow manner and cause to narrow the heat affecting zone. What happens when I uh, cutting speed increases? What when the cutting speed increases, it decreases the cutting time and to narrow the heat affecting zone, and cutting speed is inversely proportional to thickness. Okay, and last parameter is gas pressure. Okay, this sometimes we will be using right external gas. So this is also one of the process parameter focusing of lens, focal position, cutting speed, and gas pressure. Up next is the heat affecting zone. Of course, after machining, the due to heating, there will be a heat affecting zone forming. This is a simple representation on how does the heat affected zone look like. We'll be having laser coming up here. On top, there will be a recast layer. There will be debris formed, right? This cooled cooling of this whatever material using, there will be a debris form. At the exact point of bending, there will be shock wave. Further, due to shock wave, there will be micro cracks. Heat transfer will occur in this direction. This is a melt zone. And these are the various terms and what really happens on the workpiece due to the heating. Okay, this is a heat affecting zone in LBM. The heat affected zone may lead to undesirable effects such as fatigue resistance, surface cracking, and distortion. Right? It cannot go well all the time due to the heating. It could cause fatigue resistance and surface cracking. The further heating would cause the cracking along the material, right? And distortion. So heat affecting zone width increases with increase of laser beam power throughout the range. Okay, it's directly proportional to the width. Okay, heat affecting zone width increases with the increase of laser beam. Okay, and also it increases with the increase of the pulse frequency that coming up from the discharge tube. Okay, and laser beam diameter has a negligible effect on heat effect on depth. Okay, it doesn't matter what is the laser coming, but we are focusing on a particular point, right? So laser beam diameter won't have much effect on the its depth at which it is causing, and heat affected depth increases with thickness of work. Okay, if I am using a higher thickness work, I'm using a particular higher thickness work. The heat affected zone depth also directly proportional to increases. Okay, as the cutting speed increases, the cutting time decreases and less time for heat to diffuse and narrow the heat affecting zone. This point we already discovered earlier, right? So these are all the uh, points or what really the factors affecting heat affected zone in an LBM. Okay, this is all about laser beam machining. Okay, thank you.